name two jumps at 125. Oh, I'm sorry. For selling her two jumps at 125 per jump, they are making an extra of $30. Okay, next question. Now it says find the equilibrium point and the consumer and producer surpluses at that point, which is a totally different point. Assume that Beth makes no more than 5 jumps. Explain what the equilibrium point represents. In which the equilibrium point is where everybody's happy. She's willing to pay, they're willing to sell to us, to her. Okay. So in order to find the equilibrium point, we have to set the demand and the supply functions equal to each other, as we did a long time ago. So let me dig up my demand. So 7.5 x squared minus 60.5 x plus 254, and the supply is right there, 15x plus 95. Okay, so I have 7.5 x squared. I subtract, so I have negative 75.5 x, and I subtract, and I get plus, that's a 9 from 4. It's a 5 and 1. Always correct my numbers, please. Of course, I'm not going to spend my time because we have a poly feature here. So let's do that with the apps and number 9. And polynomial, yes, but it has to be arranged like that. So I had to arrange it anyway. Okay, so the first coefficient is 7.5. The second coefficient is negative 75.5. And the last coefficient is 159. 159 in the correct order, everything. So now solve. Okay, so x equals 3 jumps. They said not more than 5. So the other one you can disregard. I'm going to write it 7.06, and I'll say no, because x has to be less than or equal to 5 as they told us. So this is the only answer. In order to write the equilibrium point, I have to find the y variable. So 3 comma, and I plug it in. Right? It doesn't matter here or here, they are the same for x equals 3. So 45 plus 95. So what do I have? 150? So this is the equilibrium point, which means when we look at the demand and supply, so this is 3 and this is 3 and this is $150 per unit, and this is units. And let me mute Tess. Sorry about that. Sorry, Tess. So this is the demand and this is the supply. I'm just graphing. I don't really care. Good. So this, let me use 2 different colors. So on top of the rectangle, we have the consumer surplus. Right under, inside the rectangle, but right under the consumer surplus, we have the producer surplus. We know that we are really paying 3 times 150. So the product is 3 times 150 for the rectangle. Let me use a different color for the rectangle. I don't want to put too much here. So this. So this is a rectangle. Okay, so that's $450. So 2 things. Consumer surplus will be the integral, because it's all this area from 0 to 3 from the demand function. What was it? 7.5 x squared minus 60.5 x plus 254 dx minus from all this area. To get the red area, I have to subtract the rectangle, which is 450, and I will get a number. And the producer surplus is the rectangle of 450 minus this area under the S. So the integral is still from 0 to 3 from, what was it, 15x plus 95 dx. These will not be the same numbers we got before, of course, because this is for 2 jumps. And this was the consumer surplus for 2 jumps. And this was the producer surplus for 2 jumps. So, of course, they will not be the same. So, again, I'm going to use the graphing calculator to get these 2 numbers quickly so we can move on. I would never do that to you, but I have no choice. Okay, so the first one is the integral from 0 to 3 from a 7.5 x squared and minus 60.5 x and plus 254, and of course dx, and of course minus 450. But this is the consumer surplus. Aha, we expected more because now from 2 jumps to 3 jumps, the price decreased. Okay, good. And now the other one is 450, which is the same because it's the equilibrium point. It has to be the same with this. Minus the integral from 0 to 3, of course. And then we have 15x plus 95. And of course dx. No look at that. Okay, so enter, and this will be the producer surplus selling us 3 jumps for a total of 450. Okay, so 97.5. And that's all I had to say about this section, unless you want to work on something else. Unless you want to practice or you want to do another work on another example. That's all I. Yes?
How did you get 150? The 3 times 150? How did you get 150?
So 3 times 150. So 200. Oh no. 300. Oh, what is it? So 300 plus 150.
That's what I was saying. It's 140. It's not 150.
So 3 times 150. Okay. Am I wrong?
No, it's 1. No, I'm asking a different question. I'm asking how you got the 150 because I understand how you got the 3, but I don't understand how you got the 150. I know you did 5 plus 95.
Okay. So we have to, in order to determine the y value, which is the price per unit, I have to replace x by 3 either here or here. So 3 times 15, I got 45. 45 plus 90.
Okay.
Yeah, so I just thought that maybe there was it an error?
No.
Yes, I have to plug it in because when I set them equal to each other, if we remember in the review, first chapter R, so when we determine x by setting them equal to each other, I still have to determine the y. Because if I don't determine the y, then I don't have a point. So it doesn't matter if you plug in 3 here and you will get 150, or you plug in 3 here and you'll still get 150. Did I?
That's my question.
Okay, awesome. So is that clear now? I thought that maybe I had an error and that was not 450. Okay, good. Awesome. Thank you for the question. Other questions here? Do we understand how the consumer surplus and producer surplus work? and how we determine them? Do we need other examples? Can I move on and try to finish chapter 5 then? Okay, you can always stop me and we can always look at something else. The second application here of integration, 5.7, the last section, we only look at 5.1 and 5.7 in chapter 5, is differential equations. So we know what a differential is. It has something to do with the derivative. And we know what an equation is. Something on one side and equal to another. So basically what will this be is equations that have derivatives in them. Okay, they have multiple applications. So I would like to start by looking at a very simple situation on page 535. I'll let you choose 535. Okay. I would like to start with an illustration because we don't know how they even look like yet. I would like to illustrate with something like problem 9 or problem 10 or problem 11 or 12. So let's choose between 9 and 12.
You do something like simple?
Just you choose or I'll choose.
I don't know which one's the simplest.
Okay, so let's start with 9. In 9 we are asked to show that y equals x natural log x minus 5x plus 7 is a solution of an equation that has the second derivative of y minus 1 over x equals 0. So in this first problem, we are basically looking at how a differential equation looks like. So here another example. First derivative plus twice the second derivative minus 3 times y equals 0. So we have a function that is differentiated here, the first derivative plus twice the second derivative of the same function minus 3 times the function equals 0. Find y. This is a sophisticated situation. We are not going to deal with this in this class. It's not part of this class. But this is an example of a differential equation, an equation that has derivatives in it. This here is an example, but a very simple one. We are not asked to solve. We are only asked to show that this function is a solution. It satisfies this equation. That's all we're asked to find or show. Just show that this plugged in here as the second derivative only. I don't have the first, I don't have the function. This is the equation given to us. The second derivative of this minus 1 over x will be 0. So just check. Okay. So I cannot check anything before I find the second derivative. And now I realize that I lost track of my numbers here. Sorry about that. 1 second. Because I don't want to scan them in the correct order. So first I have to find y prime. I have to be very careful because this is the product rule. First function, second function. First function prime is 1 times natural log x plus the first function times the second function prime, which we know is 1 over x, minus 5. Of course, I'll simplify 1 and 1, and I have 1 minus 5. So then y prime equals natural log x minus 4. Good, but not good enough. I need to find the second derivative. Plug it in and see if I get 0. If I don't get 0, I'll say this is not a solution of this. If I do get 0, I'll say yes, this is a solution of this differential equation. Okay? So the second derivative is 1 over x.
Real quick, can
Yes.
you go over how you did everything after the natural log of x And then like,
X times 1 over x is 1, and 1 minus 5 is -4.
where did that come from?
This?
The plus all that stuff, not the -5, because I know that's. But
So when we
x times 1 over
differentiate,
x.
when we differentiate a product, we write the first function prime
it's
times
the-
the second
oh,
plus
okay.
the second. That's okay. So
I forgot.
that's okay. If you forgot, I'm sure there are others who did too. So let's do this again. The first function prime is 1 times the second one plus the first function times the second function prime. We simplify x, we get 1. 1 minus 5 is -4. I copied natural log and I copied -4. Is this okay now with everyone?
Yeah.
Okay, perfect. So now when I differentiate, because the equation has the second derivative, when I differentiate this, I get 1 over x. Do you think that when I write in here, replace this by 1 over x, do I get 1 over x minus 1 over x to be 0? Is this 0?
Yes.
Good. So then I'll say yes. This function is one of the solutions, not necessarily the only one, but definitely is a solution of this differential equation. And that is basically the simplest possible example. Let's see if we want to look at another. Do we want to choose another? Just to show. We're not asked to solve, just to show that this is a solution.
Maybe 12.
Okay, so let's look at 12.